everybody. Thank you for watching this presentation. This presentation is going to be around directed energy deposition technology and how we're really looking to democratize that technology and scale its usage throughout the supply chain. My name's Rob Bauman, and I'm going to take you through this presentation today. A little bit about myself. I'm a technical consultant at Autodesk. I've been with Autodesk for about 3 years now, and I'm based in the Fusion 360 product team. I work from an applications point of view on directed energy deposition technologies. I work with end users, and I work in development projects to try and develop the technology and scale its uptake in industry, really. So this is what we're going to cover in this presentation. We're going to do a brief introduction into DED. What are the variations of the technology? How does it compare to other metal additive manufacturing technologies? And then we're really going to look at where the technology is today, who's using it, why are they using it, what sort of products are they making, what machines are they using to make these products, and really what are the barriers that they're seeing and what's causing them to fail to scale this technology today. Then moving on from that, we're going to look at how do we overcome some of those barriers and how do we really drive that adoption of this technology throughout industry and throughout manufacturing so that products can realize the benefits of this technology. So giving you a brief introduction to DED. DED is one of 7 additive manufacturing technologies. So this is a very high level view as defined by the ASTM standard. There will be a few familiar technologies in there if you're familiar with additive manufacturing. Some of the more commonly used ones are such as powder bed fusion, which is where we're using a laser or an electron beam to melt together fine metal powders. And material extrusion. Material extrusion is a polymer-based technology where we extrude molten polymer to create layers of our component, and this is usually seen in low-cost desktop 3D printers. We are going to be concentrating on the bottom right-hand corner of this diagram today, and we're going to be talking about directed energy deposition technology, or DED. Now, this is a very simple view of the world of additive manufacturing. In reality, there are a plethora of technologies out there. In each one of those categories we just showed, there's lots of different subcategories, different variations of how the technology is applied, and this gives us different technologies that we can use to manufacture our components, some being more advantageous in terms of speed, some perhaps in material, and some perhaps in cost. We're going to focus in on the right-hand side of this diagram, and we're going to look at DED. We can see on here it shows 2 types of directed energy deposition technology, but in reality there are many more than that, and there are now a number of OEMs and providers of this equipment that are available to us. Now, directed energy deposition technology is primarily made up of 3 things. We have a manipulator that will move the processing head. This can either be a robot or it can be a gantry. We then have a material feed, and that material feed can either be a metal wire or it can be a metal powder. And we then have a power source to enable us to melt that material feed. And that power source can either be an electron beam, a laser, or an electric arc. And it's the combination of those 3 things that make up the common types of DED hardware that we see on the market today. So the first one of those, as you can see here, is an electron beam gun plus a wire feedstock. The next one is an electric arc plus a wire feedstock. The third one is a laser plus a wire feedstock. And then the final one is a laser plus metal powder. And these are probably the 4 most common types of directed energy deposition technology that we see being used on machines and in industry today. You can see there are a few other differences between the technologies. So for instance, on our arc wire diagram there, we can see the material being fed in from the side. And if we look at our laser powder diagram, we can see the metal powder surrounding the laser beam. This is what we call a coaxial system. So if we compare DED to other metal additive manufacturing technologies, we can see there are several differences. Traditionally, DED is used for making large components, This is because in DED, we're depositing kilos of material per hour, whereas in other metal additive manufacturing technologies, we may only be depositing grams of material or consolidating grams of material per hour. So we can make large parts and we can make them relatively quickly. But the trade-off there is that we don't get the fine detail and resolution that we see with powder bed fusion technologies. So we can only make larger parts and we can't get the small detail that we see with powder bed. Other advantages, because DED is a deposition method of additive technology and not a consolidation method of additive technology, we can mount a deposition head to a gantry or a robot. This means we can control the deposition in multiple axes, which means we can manipulate the part as we build it, therefore overcoming some of the issues with technologies like powder bed fusion, which require support structures. If we can manipulate our part to remove the overhang angle, we can, in theory, build our part without support structures. Because this is a deposition method as well, we can use multiple materials to build a part because we can simply swap the material during the building process. And finally, we can start with a pre-existing component. Because we can mount this into a machine tool, we can put any existing stock into that machine tool and we can deposit additional features onto that component. We don't have to start with the same plate every time and start from scratch. So that was a very brief introduction to the technology. Now we're going to look at where DED as a technology is today, who's using it, why are they using it, what sort of products are they making, how are they making it, so the specific machines that they're using, but what are the hurdles that they're still facing in their industries today. So we've worked in this technology for several years now, and we've worked across a range of industries from marine to aerospace to automotive, oil and gas companies, and also heavier industries as well. And these industries are all vast consumers of manufactured products. They manufacture a lot, and they tend to be larger structures, and the products that they make tend to involve a lot of energy and a lot of material to make. These industries as well also have incoming restrictions and a lot of pressure on them to become more sustainable. So they need to make their products in a more sustainable way. So they're looking for new technologies such as additive manufacturing, such as directed energy deposition, to enable that sustainability in their products. And that happens in a couple of ways. They're looking at shorter production lead times. On some of these large components, they have extremely long production lead times waiting for castings and forgings. So can they supplement that incoming material with a directed energy deposition version of that casting or forging? They're looking at reducing their material waste. Can they additively manufacture a part that's close to the net shape so that when they come to machine it, they're only removing the smallest amount of material possible? They're looking at improving their part performance. So can they take the design freedoms of additive to change the geometry of the component to improve its performance? Or can they add novel materials on top of an existing surface to improve its performance? And finally, they're looking at decentralizing their manufacturing process. So traditionally, factories were only located in one area and their products were sent all over the world to be consumed. But now, can you decentralize that factory and produce the product where it's required? So what are they actually making? So I've split this into three categories. The first category here is products that are supplementing that existing supply chain. I mentioned before, in a lot of these industries, they use large castings and large forgings that can have weeks, sometimes months lead time on top of them, where simply we're waiting around for this product to come in. Can we supplement that part of the supply chain and produce a DED version of that casting or forging so that our development cycle is significantly reduced, our production cycle is significantly reduced from design of conceptualization to delivery of the product? We're also seeing a large uptake in repair of components and reducing the amount of spare parts that industries are keeping. The marine industry is a very typical example of this. They have a boat that's sat in a dock, and that boat may have a broken propeller or a broken component, and therefore it can't go anywhere. To mitigate this risk, what the marine industry do is they keep large warehouses of spare components for the one day that they might need to replace out that part. But obviously that's extremely inefficient, and you don't know if you're going to ever need that component. So they're looking to directed energy deposition as a technology to replace that warehouse so that they can produce the specific component they need on demand, where it's needed and when it's needed. In addition to that, companies are looking at extending the life of their products, high value products, by adding new material on worn surfaces of parts that have come out of service, adding that new material, machining that part back to its original specification and putting that component back into use, reducing the overall material wastage and increasing the life of that component that they've manufactured. Finally, we see several players who are simply trying to disrupt incumbent industries that have always manufactured products in the same way. We can see a couple of examples here. The left two pictures are from a company called Pixmoving. Pixmoving are looking at disrupting the automotive industry by creating an autonomous vehicle that is manufactured with direct energy deposition. They can manufacture this vehicle on site where it's needed and reduce their carbon footprint of having to ship these components around the globe. On the right-hand side there, we can see a picture from Relativity Space. Relativity Space are trying to disrupt the space industry by creating a factory that can build rockets in a matter of weeks and months as opposed to years and sometimes decades. So what are these guys using? What kind of equipment do they have out there available to them? Well, there's a large range. There is pretty much a machine offering from every major machine manufacturer that you can imagine out there at the moment. And these range from gantry-style CNC machines to deposition heads that have been placed onto robots, to hybrid machines that have deposition and milling capability, to purely deposition machines that can only do the deposition aspect of the process. These are not standardized. They're obviously built on existing machine platforms, but they all have their own approach and they often all have their own unique technology built into the head. So going from one machine to another is not a simple process. And if you're learning one machine, you're not necessarily going to be able to use another machine. If you are taking a process from one machine and you want to try and build the same component on another machine, your results may not be the same either. So the industry all sounds great. There are people using it that are interested in it. They require this technology. There are good applications out there that we can see, and we've shown some examples of that. And there's equipment that you can buy, and there's software to be able to drive that equipment. So why is this technology really not taking off? Well, there are still a number of barriers out there that are stopping it. And I've listed a few down here. So we still see incomplete and fragmented software, something that we'll get onto in a bit, but we still see silos of software that aren't joined up workflows. The process requires expert knowledge and a lot of it as well at each step. And to gain that expert knowledge, you need to have worked with these machines for multiple years and built lots of components. The hardware is extremely expensive and it's hard to come by. There's limited materials know-how, so building in one material is not the same as building in another material, and there's a huge development cycle that needs to go on when moving to a new material. I've shown some good examples here, but really there are still relatively few real-life examples where companies are using this in full production. And behind everything, behind the process and behind the hardware, there really isn't much in the way of standards. So that means the equipment is not standardized, the processes aren't standardized, the way of testing these parts is not necessarily standardized. And all of this is leading to a failure to scale this technology in a good way. So all of these barriers have created a failure for this technology to scale. And what that means is industries that could benefit from using this technology aren't realizing that benefit. So the question we ask ourselves is, how might industry gain access to DED technology so they can manufacture their products with it and realize the benefit of using this technology to make those products? To achieve that scale, really we've got to drive the adoption down the supply chain. The industries that would benefit most from this technology are made up of vast supply chains, not just 1 and 2 tiers, but 3 and 4 as well. And for years, we've worked with the guys at the very top of those supply chains. But to get mass adoption and to get the critical mass the technology needs to be successful, really, we've got to drive that adoption down the supply chain to the lower tiers as well. But to enable that adoption, to get those guys at the bottom of those supply chains interested, we've got to overcome those current barriers that we've already spoken about. So as a reaction to this, we've put together these 4 key pillars that we want to concentrate on and we feel industry should concentrate on to try and overcome those barriers and drive this adoption down the supply chain. Now, those 4 key pillars are around the hardware. This is working with and enabling low-cost and accessible machines. Around the software, creating accessible, integrated software workflows. With people, creating tools that reduce the amount of specialist knowledge that people need to have. And looking at the process, making robust and reliable processes so we can achieve those first-time right builds. Now, if we look at the hardware in a little bit more detail, we need to make hardware that's accessible in terms of cost, but also in terms of the amount of knowledge required to drive the machines. We need to create hardware that is robust so that we have repeatable builds and we have reliable hardware that's not going to be breaking down on us all of the time. And really, those 2 things could be helped by driving standards in the area as well. There are very few standards for DED machines and hybrid machines. But if we drove specific standards in this area, we would see more robustness, repeatability, and reliability in these machines. But we would also reduce the learning curve from machine to machine. If you learnt machine A, in theory, you could move to machine B and still be a relatively competent user. Akin to that, if we moved the process from machine A, we built a part on machine A, and then we went to build it on machine B, we would be closer to getting the same result on both of those machines. So as Autodesk, we've worked with a wide range of machines. We've worked with pretty much the entire spectrum. And traditionally, we only really saw machines on the right-hand side of this scale. These machines are difficult to access. They have a pretty high price tag, and they require several experts to be able to run them. What we're seeing coming into the market now, thanks to some technology advances, are machines on the left-hand side of this scale. These are machines that are more accessible in terms of their cost, but they're also more accessible in terms of the amount of people that you need to run them. So we're making an active focus to support these machines and make sure that they grow in their scale and their use. What we can see, though, is there's still a divide between these 2 machines. On the left-hand side, we have predominantly deposition-only machines. And then on the right-hand side, we have some hybrid capability also. So what we're doing to try and bridge that gap is we're actively working with a couple of partners to produce a demonstration machine which shows hybrid capability at a level that's never been realized before. When we move on to software, we have some similar themes. We want to make software that's accessible. Again, that's in terms of cost of a user being able to get hold of the software, but also in terms of use as well. We want software to be integrated. So whatever tools, whatever capability you're using in that software, we want that to be in a single location, and we want that to be a cohesive experience. And we also want software to be connected. So we want the workflow to be connected. We want the software to be connected and be able to talk to your machine. But we also want it to be connected to your mobile devices so that you can retrieve your data wherever you may be, whatever time of day it is. And really, as Autodesk, this is our biggest space to play. This is where we can have our greatest impact as a company. This is a traditional workflow for DED, really, and hopefully some people listening to this presentation will recognize it. We take a part that we've designed, we then redesign that for the manufacturing process, so we remove features we can't build, we add stock onto the component, for example. We do our additive toolpath planning, create our toolpaths in our CAM software. We might do some process simulation, so this will show us the heat buildup in the component during the deposition process. It'll also show us the distortion in the component so that we can see if we have enough stock on our part to get to the final shape. We can do some machine simulation, so this will show us the kinematics of the machine. It will show us issues around collisions and gouges during the process. We can order our toolpath, and then we can create our G-code, and then what most of us do is we stick it on a USB and we go to our machine and we start building our component. Now at Autodesk, we have a range of products in our manufacturing portfolio to support all of those stages. With Fusion 360 and Inventor, we can do our CAD design. With PowerShape, we can do our design for manufacture. With PowerMill, we can use PowerMill additive capability to create our toolpaths and to do our machine simulation and to post-process to get our G-code. And with NetFab, we can use the NetFab simulation utility to do our thermal and mechanical simulation. Now, this is great. It's covering the entire workflow, but we still realize that this is a bunch of discrete solutions that can be quite confusing for a user on which solution they need to use in which part of the workflow. And that can cause mistakes. And really, we want to avoid that. So that's why we're actively working on taking all of this capability and joining it in one innovative platform that enables you to move up and down that workflow with seamless data transition, having all of the solutions in a single location to avoid any of that confusion, minimize the mistakes that are being made, and optimize your workflow. When we think about people, really this is giving people access to content so that they can upskill themselves and they can learn about the technology. Having accessible content and courses online or in person is extremely important to scale the knowledge that people require to be able to drive this sort of technology. And trying to do that in an innovative way, so not necessarily just face-to-face classrooms, but having it online, allows us to scale it in a way that we need to. Also, having communities of users and access to experts enables people to ask questions and solve problems very quickly, which previously would have put them off from using the technology. We're laying the foundations in our software to enable some of these things. So giving people the ability to upskill themselves, we have tools in software like the Learning Panel, which can teach them about new workflows or teach them how to use the specific tools. But wouldn't it be great if this could also teach them about the manufacturing process as well? Moving on to the bottom right-hand side of this slide, this is showing a tool called the command map. And the command map essentially maps out all of the commands that you've used within software. So it gives you a little bit of a skills matrix of where you might be proficient in the software and where you might be lacking. So it gives you an idea of where you need to focus your learning time to become more rounded and proficient in the entire software suite. We also have a growing community of users on our forums who are everything from hobbyists to expert users, but we find they are very responsive and they are very engaged, and it's a great location for people to start learning about the technology, but also ask more advanced questions. And these forums are monitored by the experts here at Autodesk, who can also help answer and solve some of those questions. One area where we do see a lack of growth, and we do need more growth, is in accessible content and courses that people can use and consume. We see several companies and organizations out there that have more formal training programs now, but we do need to grow this area, and we also need online courses that people can access if they can't travel to or go to face-to-face courses. We're trying to do this with some of our Autodesk partners and having a network of partners who can provide training, so you can come to us and we can tell you where you can go and get applicable training for the skills and for the technology you're trying to learn about. Finally, we come onto the process, and really we've split the process into 3 questions that we see users ask us and ask themselves during their experience of using DED. The first question they always ask is, where do I start? How do I know what parameters to use, and how do I know how to build this part to begin with? The second question is, once I've programmed it, will it work? How am I going to know if it's worked? And then when I built the part, how did it go? We look at the component, we say, yes, it's good or it's bad. Does it adhere to the specifications that I started out to begin with? So we're looking at a number of areas to try and address some of these questions. So when we think about where did I start, can we embed knowledge of the process into our software? Can we have more process-aware toolpaths? Can we have a way that software can guide the user on building a certain component? When they think about material parameters, how do they get access to material parameters? What parameters do they start with? Sometimes a manufacturer will give you parameters that will be a starting point, but this isn't necessarily commonplace. So can we think about potentially in the future having something like an open market where we could purchase parameters or we could share parameters with each other, at least to give us a starting point? When I think about will my process work, we're developing software tools that will enable you to predict the process that's going to happen. So we're using simulation to be able to predict the heat buildup in our component. And from that heat buildup, we can also see the distortion that we will likely see in our component as well. And this gives us great indication as to whether that component is going to build correctly, whether we're going to put too much heat into it or whether we're going to distort too much and we're going to get a good part out or not. When we get to the end of our build process, really we want to rank or rate how that process went. Did we have a successful build? Does the part look good? Or did we have a failed build? And from gathering that knowledge around the process and the experience that we've had, can we learn for next time so that we don't repeat the same mistakes if we're building the same component? Or if we're building a similar component, can we learn what we should do better next time or what we should change in the process to increase our likelihood to have a successful build? And finally, where does somebody go to learn about the best practices? Can we develop new standards where somebody could take that standard and they could see how they should be running their process or how their machine should conform or how they should be testing their components afterwards so that we have a more standardized method across the industry? So we've covered a lot of ground in this presentation. We started off by giving an introduction to DED as a technology, what the variations of that technology are. We then looked at what industries were using this technology to build components and why they were trying to do that and the sustainability issues that they have with their manufacturing processes they're trying to overcome. We then looked at specific examples of what they're making and what machines they're using to make it. But then we asked the question, so why aren't more companies and more industries adopting this technology? And we looked at the barriers that still exist today and that are in the way to stop that scale of adoption. We went on to say that there are vast supply chains out there that feed these industries. And really for the industry to benefit from these technologies, we need to drive this technology down those supply chains. And to do that, to enable that adoption down the supply chain, we need to overcome those current barriers. To overcome those, we put together these 4 key pillars that we think we need to target. Those are hardware, people, software, and processes. And by targeting these and developing technology in all of these areas, we feel that we can produce a product that is accessible to industry, that is accessible to the supply chain, that will scale this technology and enable more manufactured products to realize the benefits of producing their parts using DED. We know we can't do this on our own though. So really, we're asking for and looking for collaboration for people that work in this space and are also interested in this motion of scaling the technology to work with us to try and do so. So please reach out and get in touch. Thank you for listening to this presentation, and I hope to speak to you all soon.